Okay, thank you very much, and thank you to all the AiiDA team for the organization. I think that this is a terrific opportunity to extend to advertise what our high-throughput method and how they can be used. So my talk will be slightly different from what you have seen so far. I'll try to be a little bit more philosophical initially, and then I will try to provide few examples where high-throughput methodology were applied, try to pinpoint to the kind of style that the different methodology that you can use for the different methodology. And I always start during this troubled time with the slides talking about the Obama administration that in 2011 launched what is called the Material Genome Initiative. And in the US, this was the driving force, the financial driving force behind all the work that we have been doing in high-throughput calculation. Of course, material genomes is not just theory, and the purpose is to discover, develop, and deploy new material. So this is politics talking. They wanted to actually have material that could be used in defense and in industry. And in addition to deploy material, they list a range of technology that they want to advance, and the fact that they want to do that faster. Okay, this is where high-throughput comes to play a significant role, and this is both on the experimental and the theoretical side. Of course, we are not at this level, but is something that we have to aspire to. Okay, so this is from Iron Man, and is Tony Stark. The audio is not working, but is Tony Stark grabbing elements from the periodic table, using his own intuition, packing them, and creating a new material for his armor suit. Okay, so this is what we want to do, right? We are not there yet, but since 2011, we did develop a lot of methodology. And those methodology are based on the fact that we have an enormous configuration space involving structure and chemistry. And we are interested in mapping this enormous configuration space on a space of function that can be actually used for building device to deploy material to technological application. And for most of the, since the 50s, we have been doing the solution of the direct problem. Try to select a restricted set or even one single material in one single point in this configuration space and study the function. Okay? Study the function that that material can exhibit. And remember, here for structure and chemistry, I'm thinking very broadly, right? I'm including defect, nanostructure, interfaces, everything that you can think of. And function, I'm thinking to the actual device at the end, the one that you can use in a laser pointer or in an electromechanical energy harvester. So the direct problem can be solved in two ways traditionally. First of all is this method emphasizing development in methodology. You perfect your methodology to the point that you can capture the function that you are interested in with great accuracy. Okay, this is very important, is what is pushing the methodological advances that we had in the field in general, and is unfortunately not transferable to the large configuration space that we have there. So we need to work on restricted set. So there is another strategy that we can use to solve the direct problem. That is the one of not focusing on the quantitative aspect of the calculation, but focusing on the qualitative value that set of calculation may have in revealing what is going on from the physical point of view. So that is the methodology. This is a model that we called based on descriptors, design rules, depending who we're talking to. But what we are after are phenomenological rules that can give some insight on why a material is performing and giving you design criteria to actually mimic that functionality. Okay, so this is the solution of the direct problem. In reality, we want to solve the inverse problem. This is mathematically very ill-defined, and it's not possible to solve this rigorously. And even in the solution of the inverse problem, we have two strategies. D1 mimic I1, right? So we can hope for the improvement in computer and in methodology so that we can actually scan brute force a large configuration space until we get what we want. That is practically impossible. We can always restrict our searches when we aim to do that. Or we can adopt a bottom-up approach. If we distilled sensible descriptors during the solution of the direct problem, we can use those to design new material and build up what we want. And that is the philosophy, the approach that I prefer. And this actually, you know, it requires by nature an interaction with the experimentalist. And this also favors the fact that we can actually talk to the experimentalist. Because we don't give them a number, we give them a rationale why one material can be good or bad. Okay? So this is the general picture. And remember, this is valid for theory, but not just for theory. The same discussion that I just done could be applied to experiment. And there is a history of high-throughput synthesis, high-throughput characterization that, you know, sometimes we as a theorist, we tend to forget. So the concept of descriptor needs to be clarified a little bit. And so I want you to think to a descriptor in a very general sense. It may be qualitative. It may be semi-quantitative. It may be strictly quantitative. Okay? The point is that it's a quantity that you can calculate very easily as possible, and contains sufficient information that is telling you what the material is going to do when you go back to the lab. Okay? So it's difficult. It's not a trivial task to find descriptor, but whenever you approach an high-throughput project, you must think, what quantity are you computing? This is a little bit what comes from the big data community, right? The question comes first, and when you have the question, you can actually design your calculation, your approach, so that you can answer to that specific question. So I will follow this strategy, and I will base my discussion on three pillars, the three pillars of high-throughput research. The first is data generation, and you learned that very well. I assume that you all are very skilled in actually performing high-throughput calculation using AiiDA. Okay? And the second pillar is data repository. The data that you are generating needs to be archived. And this seems trivial, but you know, when you think to archival for telling when the data, if the data are good enough, or archival for reproducibility of your results, this is not completely trivial. And once your data are curated and archived, you want to do some data analysis, right? And I will focus on two aspects of data analysis here. One is how you query and search in your possible database. You know, and this is part of a game that we have to do in order to reach a larger community. And second, I will try to present a few examples of descriptor on few application projects that we work on. Okay? So the key for the second project that I want to stress here, that is the project on thermomechanical property, is verification and validation. And these are ISO 9000 keywords that tells that your data needs to be sensible from a theoretical point of view. You need to check cutoff, convergence, all these things very well, and needs to be validated with respect to experimental results. Okay, so these are the things that I will try to touch. And of course, I will focus on theory, and I will stress the theme of structuring intuition, right? That is this idea of developing and using descriptors. And I will try to do high throughput at different level, right? I will show results where we did high throughput of 4,000 calculation, high throughput of smaller set of calculation, but the spirit is always the same, right? We look at trends instead of looking at the specific outcome of one calculation. So there are many infrastructure that can be used to data generation. Here I'm listing few. AiiDA, there is PyMatGen for the material project, ASC from Denmark, QMPI from Northwestern, and the HTTK tool, the high-throughput toolkit from Linkoping. This one is, I participated in the early stage of the development, so I will use some results from that were developed with the HTTK toolkit. Data repository available, and I hope that I counted all the community, but I'm not for course sure. The data repository available are the material project, that is one of the largest. AFlow, that is the one that I'm working with, and material project are the largest. And then there is the computational material repository in Denmark, the Open Quantum Material Database in Northwestern, the Open Material Database in Linköping. Those are usually paired with the data generation tool. The T-Code in Cambridge, Nomad in Berlin, that is not really an independent database, an aggregator of different databases. So the number that you have seen yesterday on the number of entries in Nomad is not realistic, right? Because it's assembling data from many different databases. And the material mine in Dublin, those Stefano Sanvito independent database. And then there are tools for data analysis. And those span on a wide array. So we have MAI, that is a machine learning strategy developed at Northwest. We have the inverse design tools developed by Zunger in Colorado. These are API, the material project API to actually extract information. There is a tool developed by Los Alamos that actually integrates experimental and theoretical data. And there is this new recent effort that Giovanni is involved and AiiDA is involved about finding a way to probe the information in all the database with a single query. So I will focus on the work that I've done using AFlow or AFlowPy, that are our two infrastructure. The repository that we have, that is www.aflow.org, and our search interface, search API, that is called AFlux, is portable in principle to many other databases. And I will not get here, but this is something interesting that we are trying to develop now, that is computational geometry applied to the space of data, material data. Okay, so let me acknowledge the collaboration with several members. You have seen these slides before from Stefano, in the Stefano talk. So our group leader is Stefano Curtarola. Duke is the one that gets all the money. And then I work closely with Marco Bongiorno Nardelli. I have collaboration with experimentalists at UMD and several theoreticians across the group. The work for the material network, the computational geometry, is done with the group at Texas A&M. Okay, so let's move on and try to start dealing with an application. And the first application I want to discuss is based on the concept of chemical substitution. Okay? This is the easiest way to think to an high-throughput project. You decide a certain structure, for instance, and you start playing chemical substitution on it. That is the easiest way. You have seen this in the talk of Stefano Sanvito when he was using the Euler structure and tried to populate the Euler lattice with all the possible chemistry. So we did that long ago. This is a work in collaboration with Ricardo Armiento and Boris Konzinski and Gor Seder, and we did it long ago. And what our task was to replace lead in piezoelectrics. Okay? So we had constraints given by the company that was funding us, Bosch, and they wanted us to work on perovskite in order to mimic the property of PZT, that is a solid solution between lead zirconate and lead titanate. So what we did is try to set up a high-throughput calculation that could provide us with a new tetragonal system and a counterpart without lead that we can use in a phase diagram to create what is this region between rhombohedral and tetragonal phase that is called the morphotropic phase boundary. So we have two tasks here, finding a tetragonal material and finding a morphotropic phase boundary. These are two slightly different goals, right? And in the perovskite structure. So what we did is, as a start, we take the ABO3 structure, supercells of it, and we start populating with all the possible A and B. We kept only oxygen. Okay, so we had almost 4,000 calculations, and once we did all this calculation, we'll try to distill if we can find something new that exhibit the same property of PZT without containing lead. Okay, so how we could look at that. And this is 4 criteria, 4 descriptors that we develop across the year, right, by doing the solution of the direct problem a piece at a time. And so, for instance, these are very qualitative descriptors. We wanted to have an electronic structure that can support ferroelectricity. So it has to be an insulator with D0 orbital in of the transition metal. Then we have coexistence of rhombohedral and tetragonal phase, because we want to get close to a morphotropic phase boundary, right? So where the rhombohedral and tetragonal phase need to be competing energetically. Then we want to have a change of symmetry from rhombohedral to tetragonal that is smooth enough. So we need to enrich the phase space on path that can allow to join the rhombohedral and the tetragonal distortion. And this is done through rotation, octahedral rotation and tilting. And then we need to have a large piezoelectric effect, meaning that when the polarization, the distortion is rotating from the 1-1-1 direction to the 0-0-1 direction, there is a strong coupling with the cell, so that the cell get actually deformed and we can have a large piezoelectric response. Okay, so these were qualitative. This was done to understand what's going on in PCT. And so we need to translate those concepts in something numerical that we can put in a database, right? So our calculations were done this way, where we scan across different volumes. And the reason is that the physics of the piezoelectrics is very sensible to volume. Then we look at the energetic of rhombohedral, tetragonal, and rotational distortion. And we plot the curve. We set the equilibrium volume, the theoretical equilibrium volume. This was a decision taken a posteriori after I've done all the calculation. And we stick those in our database. Okay? Though this take care of criterion 2 and criterion 1. Okay? For criterion 3, what we did is to play a game, right? We took the ABO3 structure and we displaced the A and the B site independently. So this is a total energy response to the A and the B site independent displacement. Okay, the idea is that when we have a distortion to which both A and B site contribute, okay, we have a minimum somewhere in the middle of this diagram. When the system is mostly A site or B site, the minimum will sit here or here. So we took this, we computed all these graphs, and then we parameterized those to put them in the database. So here we are reporting the minimum along the tetragonal, for the A site, a minimum for the B site, the minimum in the phase across the global minimum on the map, and the angle at which global minimum occur. So if the angle, for instance, is close to 45, you have an idea that there is an interplay between the A and the B site. If the angle is close to 0 or 90, you have not such interplay. Okay, so we put them in the database, and then we start processing, right? So we have our total number of calculations. We went up to bismuth. Okay, this is actually very important. You know, we could not push this through the lanthanides because we cannot, at this point, trust the pseudopotential from an high-throughput point of view for the lanthanides, for the F elements. And then we start analyzing the data. This is a map that represents red for the tetragonal distortion, when the tetragonal distortion is minimum, rhombohedral is blue, and rotational is green. So you can see immediately that most of the tetragonal, the red one, are very sparse. So there are not a lot of tetragonal material. And some of this we knew from the beginning that are unrealistic. Lithium is an hypothetical perovskite. It's not a perovskitic material. Lithium niobate, for instance, is not a perovskitic material, right? So some of those are fictitious. They were just hypothetical. So the black one correspond to material that don't satisfy the criterion number 0. So they are not insulator. They don't have this hybridization. So by doing several of these maps, we filter out, according to C0, C1, C2, C3, all the possible perovskite. And so the configuration space was decimated, right? We start with 4,000 almost, and then after applying criterion number 0, we got to 99, okay? And then out of the 99 with criterion number 1, number 3, we get to 49 composition. So the good thing is that, you know, out of all this, we distill 3 families, and these are the 3 families that were known at the time. Actually, one was discovered exactly when we were working, that exhibit good piezoelectric property. By playing carefully between the pairing this, we could also come up with some new composition. Okay? But the point is that it's not, we didn't expect to make a great discovery. The reason is that perovskite has been studied so much that high throughput was not the ideal for this. This was mostly a validation process. But we validated very carefully that our criteria, C1, C0 to C3, are actually working and distill everything that we know. Okay? And this is a value. And so based on this, we pushed a little bit further. We create alloys, right? And we didn't want to do gigantic supercell, relax, testing, and so on. We thought of doing this in a strictly high-throughput way where we actually look for descriptors. And what we come up with is a sort of a interpolation between the property at the endpoints and study the stability and the tetragonality across the composition range. So this is an example. For instance, for the alloy between tin titanate and barium titanate, we saw that if you add in tin, you lose stability, but you gain tetragonality. So by tailoring this, you can actually find material with some out-of-stability synthesis, far from the equilibrium synthesis, right? High throughput or high throughput synthesis or hydrothermal, anything that can go very far from stability, you can actually design a new material that is a lead-free piezoelectrics. Okay, this was actually good. We found a few, more than one, and this was patented. That for a theoretician is good, right? We don't believe that we can patent anything, but it was actually good. Okay, so all of this was simply done by fixing a chemical structural theme and exploring the descriptor that we know by doing chemical composition. So this is one of the things that I do most of my time. Okay? But there are other criteria that you can use. When you do that, you generate a lot of data, and you need to be careful to what data are you generating. So here there is this anecdotal story. When I started to do that, I thought to use the material project data. They were available. I said I just apply my knowledge on piezoelectric, and I use the material project data to perform my high-throughput instead of doing my own calculation. And here we realized very soon that the data in the material project could not satisfy our requirement in terms of accuracy for capturing the energetic of the perovskites. So here we need to be careful. When we generate these databases, the databases are usually done on a target, right? You do a dose for a specific project. The material project was generated for batteries. They were only interested in structural theme. And they didn't care if it's rhombohedral or tetragonal, right? It's a tiny distortion of the perovskite lattice. They care if it's a layer or perovskite or bulk perovskite. So they care on a different scale, the energetic. So the data were completely useless for us. So the energetics in barium titanate is of the order of the millirydberg. So we need to have better convergence. So this is important. Data are not good or bad. They can be good enough or not good enough. Okay? And we need to stress this every time we do high throughput. Okay? Let me move to the second point that I want to do. I want to stress the fact that when we do data generation, we need to process a lot of data at the same time. So developing tools like AiiDA or AiiFlow or other tools that actually add robustness to our calculation is essential. And this seems always often a trivial task. A lot of people will tell, oh, what is that? I have all my own script. No, managing 4,000 or million of calculations at the same time is not a trivial task. Error checking, validation, all this resubmission is something that requires tools that are specialized for that task. So here you need to achieve the 2V, volume and velocity, and you need to aim to a very robust methodology. Okay? So what we did in this project was to aim to good prediction on thermomechanical properties. And in the AiiFlow database, in the AiiFlow infrastructure, we have two ways to generate thermomechanical property. One is an automatic elastic library, and one is the automatic Gibbs library. So they are using different model. The automatic GIS library is much more efficient. It's faster. The automatic elastic library is a little bit more demanding. Okay? And we wanted to validate when I have to use this or when I have to use this. And we start a project to compute everything with all the possible equation of states and so on to see which method could be used for what. Right? This is a later development in high-throughput, but you need to be sure that your data are good enough, right? And so what we did is, for the elastic point, for the elastic method, is simply compute the elastic constant, and then from the elastic constant compute the bulk modulo, the shear modulo, using different methodology available in the literature. These are all different ways in which you can compute bulk modulus and shear moduli with, from the elastic constant. And then we have another approach that is practically based on a calculation, a fitting on an equation of states that is giving you those traditional bulk modulus, and then the calculation of the Poisson ratio. That is not, the f of sigma is not very variable, so you can use a single sigma for all the data. And that is what we did a few years ago. So when you fit the bulk modulus, you can use numerical integration to fit to Birch-Morgan, or to other equation of state. So this can all provide slightly different results. So we processed those, and then we selected 74 compounds that were available in the literature with very accurate data and of different structural themes in order to validate our prediction and tell which one was good and which one was not as good. Okay, so we compute many of these tables. You can imagine we have a lot of those data. So, and the results, for instance, for the Zinco blend or diamond structure can be seen very clearly here. So on the horizontal axis, we have the experimental data. On the vertical axis, the data computed with different methodology. And you can see that, for instance, the bulk modulus here, or the shear modulo, or this is the Poisson ratio, and the by temperature are coming very well. And are coming very well mostly regardless what kind of fitting you do, what kind of equation of state you're using, if you're using the elastic library or if you're using the Gibbs library. On the other end, the Gruneisen parameter is awful. And it doesn't capture the experimental data at all. The thermal conductivity does a little bit better. This is a Debye-Callaway model for the thermal conductivity, but this is fictitious because the Gruneisen parameter is an input for this. So this is just a coincidence that is happening for, I don't know, cancellation of error or something. So this was interesting, and in order to give a quantitative sense to those analyses, we compute the correlation in terms of the Pearson, the standard correlation, or the Spearman correlation, or just the deviation from the experimental data. The Spearman correlation is particularly interesting from an high-throughput point of view. The reason that it is not aiming to describe the absolute value. I don't care if the experimental data are far away from the theoretical data, but I care that the ranking, right, the trends are respected. And for instance, in certain cases, like the thermal conductivity, we could spot that regardless of the fact that the thermal conductivity is not too off from the experimental data, this is the standard correlation, is very off from the Spearman analysis. So that means that we could not trust any prediction on the thermal conductivity done with that model. And quantitative, we have a very good prediction of the elastic moduli. The Debye temperature is a sort of okay, but Gruneisen and thermal conductivity needs to be improved. Okay? So this is a way of doing verification and validation. Validation, again, is testing with respect to experimental data. Verification is consistency of your calculation. Okay? Let me argue a different point for verification. And here I'm proposing a tool. I didn't discuss tools that we have developed, but the development of tool is at the core of high-throughput calculation. And here is a tool to actually look at the data after that you put them in a repository. And we do have a search API that is called Flux. And the search API goes beyond the fact of looking to a material, but it gives you a specific way of searching through the database. For instance, here, this is an active link, I'll show you in a minute. You can look for those materials that contain copper and sulfur and have a gap between 1.2 and 1.5 electron volt. This will be a good material for a solar cell, for instance. You can actually click on that link that goes directly on the website and extract the information and return a JSON array with all the information that you want. Okay, so this was to search, right? And you need to trust the data. The point is, can I search to actually validate my data or verify my data? And yes, you can do that. If I find the browser. Okay, you can do that. And the way to do that is simply use the same infrastructure to extract information that tells you your data are good. So we were told at a certain point that our data were off and that we didn't relax enough well our supercell or our materials. And this was a problem with the VCR. If you look at VCR sometimes is hard to converge. So we look into the data to see if we actually were doing the right relaxation. So here with the simple Python 3 script, you can extract information from a flow and provide an histogram that tells you that our relaxation is reasonably good. This is the stress, is the largest component of the stress, and it's not sharp on 0, but the distribution is minimal. And so this is sort of comforting, and we can do this in real time to extract information and validate data across the full database. Okay? Verified data. Okay, so this is it was to stress verification and validation. Let me move on to a different model for high throughput calculation, that instead of fixing a structure, you are fixing a specific material, but you are looking into path to optimize the property of that material. The typical example is doping. And I will not bother you with the basic of thermoelectricity, but in thermoelectricity, you need to deal with heavily doped material. Okay? And you're looking for materials that satisfy certain specific requirements. They need to have large effective masses, not too large, otherwise you're compromising the conductivity, but reasonably large. Several carriers for pockets, several pockets for electronic carriers, and then large enharmonicity for mass disorder and boundary scattering for lowering the thermal conductivity. Okay? So this is a complicated task. It's very difficult. We have been trying to get a good material for a very long time. It's very hard. But so we wanted to look for a material that was good and see what we can do there to optimize the problem. The lesson was learned from lead telluride. Lead telluride has been known since the 60s, but has never been used for thermoelectricity because the doping could not be pushed at the level that we can push it now. So by tuning the doping, the property of lead telluride improved greatly. So what we thought, okay, let's remove lead because we don't like lead because it's toxic, and see if we can take tin telluride and move the Fermi level by doping and optimizing the band structure. So we took a big supercell of tin telluride, and we start processing several dopants. We got to one that we liked, that is the calcium dopant. This has the effect of reducing the formation of vacancy, compensating the vacancy by a strain effect. And it does modify the band structure significantly. It raises this band. My pointer doesn't work anymore. Erase this gap, so it creates a sort of a multi-valley, so several pockets active to transport, and is also increasing the gap a little bit. And that is good because it's avoiding bipolar transport. So this is the effect, and we searched for all of this, and we found this material particularly promising. So we went to the lab, and these are experimental data. So of course, the addition of calcium lowered the conductivity at lower temperature, because you have a scatter that you don't have otherwise in the pure compound, right? But at higher temperature, it doesn't do much. So this was interesting and promising. So we look at the thermopower. That is another important variable associated with the effective mass, and that increases substantially. Okay? So overall, the material was also good from the point of view of the thermal conductivity. And the reason is that mass disorder, here, the difference in mass between calcium and tin, is sufficient. And in addition, there are boundary scattering forming in an endotaxial way that we would be able to probe experimentally. This is not high throughput. This is trying to rationalize what we actually measure, right, before. So the thermal conductivity goes down of an enormous amount. So this material is actually the highest ZT material in the tin telluride family. Okay? And we test across many different dopants. The performance are close to 1.4 that is in ZT, that is among the highest in commercial material. And it's very good compared to many other structural themes. So this was done by random picking dopants in a tin telluride matrix. Okay, so we tried other material here. We tried gallium, and gallium good, but not so good. So it is less of importance, but still it was a result of the high throughput that we brought to the lab. Okay, I don't know how I'm with time, but so this will be my last 10 minutes. Okay, this will be my last slides. I give you more time for question, and I have a lot of things to add if you are asking. So we have data generation, data repository, data analysis as pillar. Okay, and you need to think to all of these three pieces when you set up an high throughput project. For data generation, it's important volume and velocity. AiiDA satisfies this requirement as many other infrastructure. And embed, I'm learning now to embed in every project some tool to verify and validate my results. Okay? The reason is that we are going to get bad reputation as theoretician if we don't do that and we don't provide reliable data to the experimentalist. And the thermomechanical project was the first one where we did that. The value of a repository is that we can provide reproducibility. So your data are there, and whoever is able to read the input file will be able to tell how good your data are for a specific application. And we need to stress this because this is very important. Okay? And we also provide the community service. You have seen Stefano discussing a lot of construction of phase diagrams. For constructing phase diagram, you need to have a lot of calculation. This is where high throughput started, right? And so these databases are important for certain property like thermodynamics. We have our own tool on the website that allows to create a phase diagram, binary and ternary. And there are several models that you can adopt when you start a high throughput project. It's material discovery, and you can use the brute force approach, but that is going to take a long time, right, to explore something. But you need to have a focus question, and then maybe restrict class by class and probing through chemical substitution. This is sort of a chemical optimization, both from the point of view of the doping and both from the point of view of the new material that you're forming. Here, there are a few examples of things that you can ask me about, and are things that we learn by doing high throughput calculation. The first one is that we discovered descriptors that were actually good to predict the thermal conductivity without ever computing the thermal conductivity. And this was verified experimentally. Then we sort of exploring little databases, we learned a principle of anisotropy that turned out to be very interesting and brought us to explore criteria to induce or remove anisotropy in transport coefficient, and also ways to actually compute property that are optimizing the conductivity. This is bandwidth. And of course, in doing that, we develop a lot of tools. And of course, one tool is the projection on tie banding Hamiltonian that provide band structure interpolation and several other quantity computed at very cheap cost, in addition to material fingerprinting. Some self-consistent calculation of the U, that is at least making the calculation of the database a little bit less parameter dependent. And we have a new software that we will be releasing soon that actually use the tie banding Hamiltonian that we can generate with the tie banding scheme to compute topological invariant, all these topological analyses that are actually very in vogue these days. Thank you very much.